I always loved writers. To me, they are part of the roots of old school demo scene. This one is taken from Digital Innovation by Anarchy. Maybe you noticed that I reproduced this writer kind of in my latest intro called Let It Code. And I wanted to show you the very basic bricks of my demo coding environment that I used to, yes, reproduce that effect. That demo coding system is a weird animal, which is JavaScript based CPU emulator that also emulates a part of the custom registers both for the Amiga and the Atari ST, including STE. And it allows me to avoid a lot of mistakes thanks to advanced debugging features. You will see some of them in this video. This environment is available for anyone that wants to try it. Just send me a message, especially if you're a beginner. It helps you figuring out a lot of common mistakes. Okay, now for some code, we'll start with the basic boring stuff. Everything is accelerated here because there's nothing interesting for you. Sections, I like to have different files for my sections. Yeah, I'm gonna have an neat update, of course. We will need a copper list because we're starting with some Amiga code. I'm just pasting an existing copper list here, really default screen, nothing fancy here, 1-bit plain, classic, low resolution. And one very common thing when coding OCS at least is to put the basic custom register value into ASIC custom, not color 0. And now, how do we make sure that ASICs will remain unchanged? I might not be a good coder, but I'm excellent at making stupid mistakes. So I had to find out a way to kind of assert that what I think is true is actually true. So as I told you, my system is based on JavaScript. So I found a way to insert JavaScript instructions literally in the middle of my assembly code. Of course, if you feed, let's say, VASM or DevPack or your favorite assembler with JavaScript code, it will never work. So the way I'm doing it is I'm using comments. So I'm starting with a semicolon to mention it's a comment, so it's going to be okay for your assembly. Then I'm going to type greater than JS, which tells my system what's following now is JavaScript code. Okay, hold on a second. What it means is that I can, as long as I'm developing and prototyping my effects, I can write whatever function I want in JavaScript. It can be super complex or super simple. And I can invoke it and access my memory and my registers and check that everything is okay. So I wrote tons of debugging functions. The whole list is available in the documentation. And for this example, I'm going to use the function lock that allows me to lock a register and to document why the register is locked. So typing lock, then the parameters. The first parameter is the name of the register we want to lock, which is A6. Then comes the locking mask, because I might want to lock, for example, only the 16 lower bits of my register. But in that case, we want to lock the whole register, so the mask is going to be -1 for 32 bits. And the third parameter is optional. It's an extra message that is displayed together with the error message to say, for example, why the register was locked. And now for some more boring stuff, we need to give our copper list pointer, to set some quarter coders. There you go. and let's go to the browser to see if everything is fine. I'm pressing Shift C to see if my corpus is taken into account. That's the case, we can continue. And maybe now let's try to modify A6 just to show you how the register lock works. So let's put some real value in A6, check, bam. Okay, we got our error message telling us that we shouldn't change A6 because it's locked. Okay, working as intended. Okay, we're supposed to code a writer and we barely started yet. So let's create a buffer in our BSS back buffer because we're gonna need to write the whole text in a back buffer and then reveal it using the writer effect. So we'll start by writing the text to the back buffer. So for debugging purposes, we're going to display the content of the back buffer. So we set the pointer of our bitplane to the back buffer, and let's display some pattern near the middle of the screen. So it's gonna be back buffer address plus kind of the middle line little point. Let's get back to the browser, see if it works. Refresh it, still stuck on the previous. There you go. I have my pattern, everything's fine, just checking bitplanes and colors and everything. I'm going very, very quick here. I'm just making sure everything is fine. Okay, we need a font, so we're going to inkbin it. Where is it? It's here. Copy paste the file name. Quickly checking how it looks like. It's a 8x8 font. That is here, very simple 8x8 font. So now we need for each letter to know the offset in the binary file, which is like the UV coordinates if you're doing some 3D programming. So let's go. So for the first line of characters in the font, we're going to start, obviously X is gonna be 0, so X or U, same thing. And V, so Y, it's gonna be 0 to top left character. Then we need to count how many characters we have, how many letters we have on the line in the font. So let's create a constant for that. So font letters per line. So it should be equal to, we need to count, so maybe check the file. So that's 30 letters. Okay, so we're going to repeat, guess how many times? Yep, 30 times. The same operation, which will be just increase the X, so the U coordinate for every letter. Every letter is 1 byte wide, so it's gonna be 8 pixels, 1 byte. So okay, I declare my U plus my V. V being 0 doesn't change for a single line, so it doesn't mean a lot, but to me it's clearer that way. And I'm just going to increase my U by 1 because, as we just said, it's 1 byte per letter. Then for the second line, it's gonna be approximately the same thing, except that V is gonna be different because now we are reading the second line of the font. And as we know, it's 8 pixel high, but let's create a constant, maybe. I'm gonna call it font image with bytes, yes, because we need to skip the size of a line by multiplied by the height of a character to know how many bytes we need to skip to go from one line to another. There you go. if you know exactly what I'm doing, you can definitely fast forward. Okay, we should be able to simply copy, exactly duplicate line 2 for line 3. No difference. Yep, no difference. Line 4 is just going to be a bit different because we have less characters on the last line. And yep, let's tabulate a bit. Otherwise the assembler won't be happy. And we are good. We have a font, we have coordinates. Now we can code the writer. Okay. So let's include new file. I like to separate stuff in many different files. src font, there we go. As usual, some init, some draw. Call it. Maybe before showing anything on screen. And call the draw. Okay, I don't know what to put in the init for the moment. We can. Okay. So first we need to load the UV we just created. Coordinates, we need obviously to have our font file, so bitmap data. We need to tell where we want to write to, so the destination bitplane address. Okay, so we want to parse some text and display the text in our back buffer. So we're going to read the different characters in the text, and we're going to iterate the character until we reach the end of the text. So we're going to have a line index. We're going to loop. And this is the moment I realized we forgot to type that text. So let's fix this. We will load it there. And now we're going to create it. So we're going to go to data.asm. We're going to create the text at the top of the file. We don't care. Text. Maybe before I'm going to just add some specific character code just to tell the writer to go to a new line. So there we go. I'm going to use yes. 265 is a good one, and maybe something for space also. It's just better than using a hard-coded numbers, and also space is the first character in the font, so it's going to be easier to get the offset of the character in the font by subtracting just space ASCII code. So let's center a bit the text, add some lines so that it doesn't start at the very first line of the screen. Then we're going to begin every new line with a new line command and then type the text. So we could type, for example, mcck workbench rules, which is the name of my coding environment. And for the rest, I'm gonna cheat and use an already existing list of crits. Never forget the trailing 0 to finish your string. Let's check in the browser if the emulator is still happy with all of those new lines, and it isn't. Oh yeah, odd even address problem. Of course, I just typed some text, it's bytes, so I need to add an even command here to make sure, well, that no matter the number of characters in my text, I'm still having even addresses. Okay, and finally we can fetch our first character from our greeting text. Woohoo! There you go. We fetch the next byte, store it in D0. So this is going to be ASCII code, of course, of our character. We are going to check if it's 0, because it might be the end of the text. So there you go. We're going to check what the first paste it there, and then we're going to check also if it's a new line, a specific character. So there you go, maybe it's a new line. If it's not a new line, we will continue. Go. And so if it is a new line, what are we going to do? We're going to restore our destination pointer, original one, to just increase by the size of a line. So the size of a line being a line of text, of course, not a line on screen. So this is going to be the width of my screen that I'm going to multiply by the height of my font. And there you go. And I'm going to add, say, 2 lines, so that 2 lines on screen are not stuck together and there are two spaces, two lines of 2 blank lines between 2 lines of text. Okay, store back the address, and this is ridiculous because okay, of course here I can do it this way. Okay, much better. Okay, I need to define this. Okay, this will be different on Atari, but for the moment we are doing it in a ugly way. Okay, and we are done. We can go to the next character. Now, if it was not a new line character, we need to display that character. So we're going to transform the ASCII code into a character index into the font. From that index, we can fetch the UV actually. So as our UV table is one word actually, which is an offset into the font data, we multiply by 2 that index. That could be optimized, we don't care. It's just preparing the back buffer. It won't run every frame, it's just going to be done once per text. Now we can fetch the index into the font, the offset actually, and from there it's going to be pretty obvious. There we go. This is gonna be the number of bytes we're gonna have to copy, because the characters are 1 byte wide, so the height equals the number of bytes to copy actually. So here we copy each byte of the font's character to the bit plane. And of course, we go to the next line for the source. So we just add the width of a line to the source register, source offset register. We have to do the same thing for the destination address, and then we can increase the bit plane address because the current character is written, so the next character will be to the right of the current one, so 1 byte after. And we can jump to the next character in the text. So let's see how the emulator reacts to that. And of course it can never work on the first try. Okay, oh, this is a good example of one of the features I like, as here my system is telling me, you're adding like the contents of a hard-coded address to register. Are you sure you didn't mean to add an immediate value and you just forgot the hashtag just before the address to transform it into a value? And he's right, I fucked up. Let's fix that. This feature saved my life so many times. Let's try again. Okay. Oh yeah, this is why the line was red. Okay, I get it. Comma. And yeah, -1. Fine. Let's try again. And yep, we're still not there. Oh yeah. I'm changing a locked register. Yeah. Okay, so here, different options we could unlock before changing it and then relock. Or we could cheat and tell the system, look, on this very line, I know what I'm doing, please leave me alone. And this is what we're gonna do. So as for the rest, on this very line, I'm gonna type my68K workbench, no error. And just like that, no error will be raised on this line, even if the system is not happy. And it fucking fails somewhere else. Okay. We are overwriting the code section. It says, so destination is wrong in that move. So A0 is wrong. Let's click on its value. Oh yeah, it's very, very low. Cannot be right. And so why is A0? Oh, because it's an input parameter to the function and I forgot to set it before calling it. So, okay, let's load our back buffer address to A0 before calling the function. And it might work better. Oh, look at that. It's beautiful. All right. Okay. That's not a complicated piece of code. Still, I'm happy. And now what we should do is make it work on the Atari ST also. And we're gonna say it's not that much different and there's a lot of code in common. So in my system, I need to open my config file where all of my effects are described and registered, and just say that the target platform now is STE instead of OCS, and the ST is going to be emulated from now on. Also, there's a specific define that is set depending on the platform. It's going to be target OCS for the Amiga OCS and target ST or STE depending on what you put in the file we just edited. So of course this is on the Amiga. So for ST we're just going to set the palette. So same as Amiga, some custom register address. Don't hate me, ST coders, I know I could use only the word negative version. And now let's set the values and unlock the registers. And now let's create a macro to show the screen whatever is in A0 depending on the platform. So OCS is just going to be, of course, bit plane address. A bit more complicated for STE. We have 3 bytes to set for the low, mid and high parts of the address of the buffer we want to show on screen. So yeah, There you go. So this was for the main file. Now in the data, we don't need the copper list. On ST, the rest is the same. Obviously the screen size is different. There you go. So no, you know what we're gonna use? It's gonna be better. So let's do this way. Yep, and then a single alloc here. Yep, that's better. And now we're going to tap into the code. And actually we only need to change where we're writing the bytes to screen. Obviously the data we read from the text and from the font is exactly the same, but what we write, the way we write to bit planes is different. So if we're on STE, I'm not going to explain how the bit planes work for STE here. You can find tons of documentation on the web. But basically, every time I write 16 bits, so 16 pixels, I've written 16 pixels for one bit plane, and I need to skip the 3 next bit planes. So I will need to add 3.2 bytes for 16 pixels. So I will need to add 6 bytes to my bit plane pointer every time I've written 16 pixels, which means 2 characters. So this is what we have here. The exclusive OR checks if we have written 2 characters, just to know if it's an odd or even character. Then if it's the case, we're going to add 6 bytes to skip bit planes 2, 3, and 4. Okay, what does the emulator say? Writing beyond allocated memory. Okay, let's click OK. It's here. So A0 is faulty again. My gosh. It was said this time, but it says overwriting beyond allocated memory, which means it gets too high for some reason. And I think I know the reason why, actually. See, we have this error on ST only because the size of the Atari ST screen is 200 lines high and not 256. So we just have to add some extra lines to center the text only on Amiga, so only on OCS, and just not add these extra lines on ST. Let's refresh the browser. And there you go. Isn't that impressive? Not a lot of code, and it works. Okay, as I'm happy with my shit, I just want to show you just a few, very few, very tiny subset of the debugging features. For example, the way to test that we are reading or writing in zones that are allowed for the specific routine we are using. For example, here I want to limit the CPU reads only to the font data. So I'm limiting it to the address of my font. So this is the beginning address, and the end address is the address of my font plus the size of the font file. So yeah, let's see in the code how it translates. There must be a date. Oh no, it's in the font draw. There you go. It's here. You see the limit right. We've not spoken about this one yet. This is this one, the limit read. So the read is happening here on the move byte. So what we're gonna do is play with D0 to change its value so that it's too high and so that the system is not happy. So just checking here, A3 is actually pointing on phone data, it's okay. And D0, let's put it to, I don't know, yeah. Let's go, run, trace, run, bim, hehe. Yep, I'm not allowed to read here. So now let's do the same thing for the write address. So we want to write only to the screen. So I'm going to limit the write to the address that is given to me, plus, and the end address is obviously start address plus screen size. Breakpoint the same place, this time it's A0 D1, so A0 is actually, yes, pointing to the back buffer, fantastic. Some offset because we already wrote a few lines. And well, we skipped a few lines, you know, at the beginning of the text. And D1, let's screw D1. Yeah, that's a nice random value. Let's go, bim, and there you go. I'm not allowed. Okay, same principle, you got it. And of course, if I refresh the emulator, registers get back to the initial values, so it's running. Now I'm gonna place a breakpoint somewhere in my main loop, and I'm going to reach that breakpoint and iterate a few times, then press W, which stands for where am I, and it's gonna show me what's on the stack and also the last executed branches. It shows me also, you can see times 6 between parentheses to show me how many times I've already executed this branch. So it's very helpful when you reach a crash, a bug, whatever, or breakpoint to know how you came here. Also on the bottom right, at the bottom right of the screen, you can see the last CPU reads and writes, also with the values that were read and written. Always useful to know why your program did stop here. And last but not least, we have a time machine. So if you really still wonder how you could break here, just use the Y key to get back in time, which I'm doing here. You can see that the registers and the values in memories also go back in time. And you can see, for example, the value of D0 changing. And if I press X, I go back to the future. And here I reach the maximum value.